Alright, well let's go with something a little less intuitive, just to exercise your linear of expectations brains. So let's say we have a box that contains 4 balls. It contains a yellow ball, an orange ball, a green ball, and a blue ball. You're going to randomly select 4 balls from the box with replacement. With replacement just meaning you could get 4 yellows or 4 oranges and so on. What is the expected number of distinct ball colors that you will select? So, for example, I could end up with, I don't have a yellow. Okay, yeah. So I could select a yellow, followed by an orange, followed by another orange, followed by a blue. So that would be 3 different distinct ball colors. So we could do this by directly computing probabilities. So for example, what is the probability that one color is selected? Well, the probability that one color is selected, let's just take yellow, for example. The probability that I selected yellow 4 times in a row is 1 over 4 times 1 over 4 times 1 over 4. And there are 4 different ways that I could do that. So I could do all yellow, all orange, all green, or all blue. So the probability of selecting one color is the number of ways that you could select one color multiplied by the total number of possibilities. Well, there are 4 different ways I could select one color, and there are 4 to the 4th power possible sequences of ball colors that I would select. So that one's not so bad. We could do that. What's the probability that 2 colors are selected, though? So going from 1 to 2, things get a lot trickier. So how many different ways could I have 2 colors? Well, I could have a yellow followed by 3 orange, a yellow followed by 3 green, a yellow followed by 3 blue, a yellow followed by 2 orange followed by another yellow. So there's a lot of different things to be counting there. So what we don't want to do is compute the probability of every single possible number of ball colors. So we're going to tackle this problem in a different way, a little bit in a way that I will admit is a little bit less intuitive, but the answer will be very intuitive, and it should be fairly straightforward once I give you some of the extra pieces of information. But before we do that, let me just ask you, what does your intuition tell you as a reasonable value, expected number of distinct ball colors? Well, you should almost always sort of assume the extremes aren't going to work out very well for you. And from what we've seen before, you might be tempted to cross out the exact value, so exactly 2 or exactly 3, and that turns out to be, if that's something you were thinking of, that turns out to be good. And again, we'll sort of get rid of our other extremes here, and what we'll end up with is something sort of between 2 and 3. If you didn't come up with between 2 and 3, that's not really a problem. I don't expect you to have thought of that beforehand. I just wanted you to think of a reasonable expectation before we went through the process of solving this problem. To give yourself an intuition for the answer that we're going to get, a good place to start is just to write code for it. So I'm not going to linger on this slide, so if you want to, you can pause it and type this out. But what I did was I wrote a simple Python program to run this trial. So a single trial here is going to be, what if I select from so many different colors, and I'm going to draw so many different items from it. So here in the example I've run, it's going to be 4 different colors, and I'm going to select 4 items just like the example we've run through. My code's a little more generic in case I wanted to play around with these. And I'm going to repeat that 1,000 times and just see, well, how many distinct ball colors do I end up with? And when I run this code, I end up with 2.72. So unless I have a bug in my code, our analytical solution we end up with here on sort of pen and paper should be close to this empirical result we got with 2.72. Alright, well, where do we start with this? What we're going to do is have a couple of different random variables. We're going to have a random variable for the number of distinct colors selected, and that's going to be X £, or X octothorpe, or X hashtag, whatever you want to call it. And we're going to have indicator variables that denote whether or not we've have the appearance of each color. So we'll have XY denote the random variable that a yellow ball is selected. Any number of yellow balls are selected. So XY can be 0 or 1, which again makes it an indicator variable. It will be 0 if no yellow ball is selected, and otherwise it'll be 1. So indicator variable. Then what do we have? Well, we have that our random variable for the number of distinct colors is equal to our random variables for each of the colors. So we don't necessarily expect to get a yellow every time, but if we sum up all of our individual expected indicator variables for each color, that will give us the number of distinct colors we can expect. So if we on average sort of expect half the time we do get a yellow, and half the time we get an orange, half the time a green, half the time a blue, that would be half plus half plus half plus half is 2. So we'd end up with 2 here. That's not exactly what we'll end up with, but that's the idea of this equation. Well, now we can say what's the expected value for the distinct number of colors? Well, it's just equal to the individual expected values for each of our indicator variables above. And we can do that because of linearity of expectations. And since each ball has the same probability of being selected, so that's the expected value of xy is equal to xo, xg, xb, what we really end up with is just the expected value of the number of distinct colors is 4 times the expected value of 4 times the expected value of one of our indicator variables. So all we need to do is dig into this one indicator variable xy, and we've got our answer. So that's what we're going to compute. So what are our possible outcomes? Again, our possible outcomes are just 1 and 0 because it's an indicator variable. And again, we don't really have to care about what this probability is because it's multiplied by 0. So what this problem boils down to is just trying to figure out what's the probability that we select at least one ball being yellow. Well, that's kind of difficult to calculate in and of itself because we have to take into account, well, what's the combined probability of the fact that I can get 1 yellow ball, 2 yellow, 3 yellow, or 4 yellow balls. But there's actually an easier way to do this. We can use the complementary probability. So we'll say that the probability that we draw a yellow ball, since there's only 2 possible outcomes, is just equal to 1 minus the probability that I don't get a yellow ball, which is much easier because there's only one way that I don't get a yellow ball, and that's that I don't select a yellow ball the first time, I don't select a yellow ball the second time, third time, and fourth time. And that's actually a pretty simple probability. So what is that probability? It's just, well, 3 out of 4 times, if I'm selecting a single ball, there's a 3 out of 4 chance that it's not yellow. And I do that 4 times, so I raise 3 out of 4 to the 4th power, and that's my probability. That's my probability that I don't select a yellow ball, and I take 1 minus that quantity, and I get the probability that I do select at least 1 yellow ball. So that's what we have here. But now we need to compute the expected value. Well, expected value, like we said, is just equal to the probability of that outcome. So our expected value is the same quantity. Well, now what's the expected number of distinct colors? It's just 4 times that probability. And what we end up with is 2.734, and there are more places after the decimal point, but that's all I've left us with here. So if you have any questions about this exercise, feel free to ask them on Slack or feel free to ask them during my office hours.